Good morning. Welcome to Introduction to Probability Theory and Statistics course. We are in module 11, topic 11, testing of hypothesis. We have already completed 2 lectures on this topic. In one lecture, I have completed till the testing of hypothesis regarding the population mean, and in then lecture 2 I have covered testing of hypothesis regarding the population variance and population distribution. This is a third lecture. In this lecture I am planning to cover testing of hypothesis regarding the contingency tables, and testing of hypothesis regarding proportions. Finally, we are going to discuss about the analysis of variance. First, let me brief what is testing of hypothesis regarding the contingency table. This particular test is called the chi-square test to determine whether or not two variables treatments and outcomes are independent or not. That means it is possible to make a statement about the variables involved, whether those variables are independent or not. So, we start with the null hypothesis, those variables are independent, and the alternate hypothesis is they are not independent. That means there is a dependency between those variables. So, we are going to verify, or we are going to reject the null hypothesis that those variables are independent by the sample of a random sample of size n and with the given level of significance alpha. So, as I said earlier, it involves the same 5 steps. The first step is preparing the statement, that is a null hypothesis statement and alternate hypothesis statement. Then you have to create the test statistics, that is a step 2. So, here we use the letters called we denote Eij represent the expected frequency for the cell in the ith row and the jth column. Since we are talking about 2 different random variables, therefore, the table information gives the form of rows versus column. So, the rows is going to be the information related to one variable and the columns information related to the another variable. So, the Eij represent the expected frequency. As the variables are independent by the null hypothesis, so that can be represented as the Ri, that means ith row multiplied by jth column divided by n. Ri is the expected frequency of the ith row and Cj is the expected frequency of the jth column. In other words, the expected frequency is the row total multiplied by the column total divided by the total sample size. So, here capital N is the total sample size, not the, do not confuse this capital N with the population size capital N. So, this is the way the typical contingency table look like, row versus column. This has wide applications with the health related problems. Therefore, so suppose you give a particular medicine and by providing the different treatment, how it is giving the output. That means whether the treatments are independent of the outcome or not, that is a question. Another example you can think of the students when they are performing in some particular courses, the marks versus attendance. That also you can think of whether marks versus attendance, whether they are independent or not. That also can be concluded from a sample of size n. Therefore, here the test statistics is going to be the double summation over the rows and columns of the values minus their basically the observed values minus the expected values, the whole square divided by the expected frequency Eij. That follows a chi-square distribution with r minus 1 times c minus 1 degrees of freedom. The reason is the same, like you have a r rows and c columns, and the number of independent information is going to be r minus 1 as well as c minus 1 information respectively. Therefore, you will have a degrees of freedom is going to be r minus 1 times c minus 1. So, once you identify the test statistics, then all the further steps follows as I explained in the previous testing of hypothesis. So, in detailed what is the meaning of R, what is the meaning of C, and total number of observation I make it as a capital N. You can think of a small n also, no need to confuse this capital N with the population size. You can think of a small in itself, and Nij is a observed count for the cell in the ith row and the jth column, whereas Ri and Cj's are the total for rows and total for columns respectively. Therefore, you reject the null hypothesis. The null hypothesis says that both the variables are independent. If the values which you obtained from the test statistics, if it is greater than what is the point in which the right tail probability is going to be alpha with the r minus 1 times c minus 1 degrees of freedom. As a simple problem, you can go through the problem and you can understand how we can come to the statement about these two variables are independent or not. So, the null hypothesis is these two variables are independent, and the alternate hypothesis is they are not independent, and we are going to verify this statement with the 5% level of significance. So, you can compute all the values based on the formula what I have given. You can pause and you can verify your results with the results obtained here. If at all any mistake is there, you can fix it yourself. So, for this particular example, you can able to get the Eij's for different I and j, and finally, you can get the d naught square. The d square is the test statistics, d naught square is the values obtained for the test statistics with the given information about the sample information as well as with the null hypothesis. So, because of the null hypothesis, you convert Eij into Ri Cj divided by n. So, you substitute all the values and you can get the values and you can conclude whether the null hypothesis will be rejected or not. In this problem, it is going to be rejected, and this is a one-sided test. Your alpha value is keep it in the one side of alpha as it is. So, that is the critical or rejection region. So, based on this all the values based on this given sample set and given alpha, the null hypothesis will be rejected. we will have one more example, that is a die is rolled 150 times with the following results. The question is test the hypothesis that the die is fair at 5% level of significance. Therefore, the null hypothesis is going to be the probability Pi, that is equal to 1 by 6 for 1 to 6, where Pi is the probability that the face value is high. So, we can get the d naught square using the data which you have provided. Then you can find the table value from the chi-square distribution with the 5 degrees of freedom with the 0.05, and that value is 11.07, and you can get the observed value, that is d naught square, that is 10. Since the value of d naught square is lesser than the table value 11.07, we could not able to reject the null hypothesis. Therefore, the conclusion is H naught is not to be rejected. So, this is a one more example for the theory which we have discussed just now. So, now we are going to discuss about the testing of hypothesis regarding proportions. There are many examples one can think of. Here I have presented two examples. One is a candidate competing in next elections is interested in knowing that what proportion of voters will vote in favor of him or her in the upcoming elections. And another example is that all manufacturing industries are concerned regarding the fraction of defective items in a particular shipment. Like that you can think of many more examples. In all those examples you can able to identify the problem of test hypothesis testing is that the proportion of successes in a random experiment whose distribution is binomial distributed with some specified parameter value. We are testing the null hypothesis, that is H naught, the proportion P takes some particular value, where P is the parameter of binomial distribution. So, the alternate hypothesis may be one of the usual either two sided or one sided alternatives. If the null hypothesis is P is equal to P naught, then the alternate hypothesis is P is not equal to P naught. So, there is a small mistake here, the last this one has to be P is equal to P is not equal to P naught. If the null hypothesis is P is greater than P naught, then the alternate hypothesis is P is less than P naught. If the null hypothesis is P is less than or equal to P naught, then the alternate hypothesis is P is greater than P naught. The last point, this has to be P is not equal to, the last one, P is not equal to P naught, there is a correction in it. Therefore, the appropriate random variable denoted by capital X, where the decision criteria follows a binomial distribution with a parameter n comma p, and the statistics is p is x divided by n. Now, we are coming into to test the hypothesis. You have a null hypothesis is P is equal to P naught, and the alternative is P is not equal to P naught. At this stage you have a two sided test. So, you can be able to get the P value if x is less than n P naught, and similarly you can get x is greater than n P naught. So, reject the null hypothesis if the computed P value is less than or equal to alpha. That is what we have earlier also said. If it is a one sided test, according to the null hypothesis, you have two possibilities of the one sided test. In both the cases you can able to find the p value. So, the conclusion is reject a null hypothesis if the computed p value is less than or equal to alpha. The alpha is the level of significance. There is a possibility the proportion p is equal to p naught, the p naught may not be given to you. In that case you have to estimate the value p naught. So, that can be estimated from the sample data. So, for large n, when p naught is very close to 0 or 1, the Poisson distribution may be used. Also for a larger n, you can think of approximation into the normal distribution. So, this is the test statistics. So, the test statistics is capital X minus n p divided by square root of n p times 1 minus n p. The reason is the x follows a binomial distribution whose mean is n p and the variance is n p 1 minus p. Therefore, what we are saying is for larger n, this test statistics approximately a standard normal distribution. So, we have a step 1, that is a null hypothesis and alternate hypothesis. Step 2, we have a test statistics. Step 3, you get the value of the test statistics, that is z naught, that means small x minus n p naught divided by square root of n p naught into 1 minus p naught. Once you get the value of z naught, then you compute the critical region based on whether it is a two-sided test or one-sided test. You identify the z alpha by 2 or z alpha or minus z alpha based on one-sided test or two-sided test. Then you conclude reject null hypothesis if the z naught value is lies within the critical region. For a two-sided test, it may be in the left side or the right side. If it is a one-sided test, then accordingly you can find out whether the z naught is within the critical region or not. Accordingly, you can conclude the rejection of null hypothesis. There is a simple example. Kindly go through the example, then you solve yourself, then make sure that whether you are getting the same result, and then you conclude the step 4 and step 5 also. Here I have not for a given alpha, alpha is a 5% level of significance. So, you can do the identify the critical region point, then you can go for concluding the rejection of the null hypothesis, that is step 5. Suppose you have two proportions, then also we can apply the similar idea what we have done it for testing of hypothesis for the population mean. The same thing you can extend here, it is two proportions. Again you will end up with the test statistics which follows a standard normal distribution. Then you can proceed further in the same way. And here we are assuming that P 1 is same as P 2, that we take it as a P. With that only you can get this test statistics. Same thing we have done it for when two population variance are unknown, then we assume that they are equal and then you compute the spooled variance and so on. The similar calculation here also. When P is not given, you can find out the estimate for P, that is by x 1 plus x 2 divided by n 1 plus n 2. And you can apply the same logic. Suppose you have more proportions, more than 2. Still you can apply the similar logic what we have used it for the two proportions. You can get the test statistics is going to be standard normal distribution for those k proportions, and then your test statistics now it is going to be the individual proportions is going to be a standard normal distribution, and the test statistics is going to be sum of those squares of standard normal distributed statistics. If you see it very carefully, inside the summation each term that is going to be a standard normal distribution, and we have a concept if you have a standard normal distribution, then square of standard normal distribution becomes a chi-square distribution with 1 degrees of freedom. So, the same logic is used here, and we have k such proportions, and you should not confuse here with the degrees of freedom. Here you have only k degrees of freedom, not k minus 1 degrees of freedom, because you do not have any relationship between those k proportions. Therefore, all the k proportions are independent information, you are just summing it up. Therefore, this becomes a chi-square distribution with the k degrees of freedom. That I have given the reason also. Sum of k chi-square distributed random variable becomes the chi-square distribution with the k degrees of freedom. And suppose the p naught value is not given, you are going to estimate the p naught. In that case, the degrees of freedom will be reduced by 1. So, now the reject the null hypothesis if d naught square is going to be based on whether it is a one sided test or a two sided test, it is a two sided test. So, it is basically H naught you are going to reject if it is within the critical region with the k minus 1 degrees of freedom when you are estimating p naught value. If you are not estimating the p naught value, then it is with the k degrees of freedom. If you are estimating p naught, then it is going to be with the k minus 1 degrees of freedom. Fine. So, it is not the one sided test, it is the two sided test. As a simple example, we have given a problem, and the informations are given nicely in the form of a table also. So, therefore, you can understand the example, and you can make sure that whether you are getting the same result, and the p value is not given. Therefore, you have to estimate the p cap, then use those results and make sure that whether you are getting this same answer. If at all any mistake, then there is a possibility of numerical, we would have possibility of you would have done any mistakes here. So, since we have 4 proportions, so we are making a null hypothesis, all the proportions are same, say it as p, and then we are estimating that p also. The alternate hypothesis is obviously negation of null hypothesis, and then you find out the test statistics value, identify the point in which the right tail probability is going to be alpha by 2, then you make sure whether it is going to be critical region or not. In this problem it is not in the critical region, therefore, you are not able to reject the null hypothesis. Now, we are coming into the last problem of testing of hypothesis, that is called analysis of variance. This is the last problem of testing of hypothesis, that is called analysis of variance. through one example we will come to the theory of analysis of variance. You see this example, a institute is planning to purchase in quantity one of 4 different tutorial packages designed to teach a particular programming language. Some faculties from the institute claim that these tutorial packages are basically indifferent in the sense that the one chosen will have little effect on the final competence of the students. To test this hypothesis, the institute decided to choose 100 of its students and divided them randomly into 4 groups of size 25. Each member in the ith group will then be given the ith tutorial package to learn the new language. That means the total sample of 100 students is divided into 4 groups and each group is given the particular tutorial package to learn. Once the semester is over, the comprehensive exam will be taken. The institute wants to analyze the results of this exam to determine whether the tutorial packages are really indifferent or not. Basically, we have 4 different tutorial packages. We want to know whether they are really indifferent or not. That is what we are going to test. As the students are distributed randomly into 4 groups, it is probably reasonable to assume that the score of a student in exam should follow approximately a normal distribution with parameters that depends on the tutorial package from which he was taught. That means each group, that information follows approximately a normal distribution with the parameter that depends on that particular tutorial package. And also it is reasonable to assume that the average score of a student will depend on the tutorial package and he or she was exposed to, correct. Whereas, the variability in the test score will result from an inherent variation of 100 students, not from a particular package used. That means there is a possibility of the mean will be of function of mean of as a function of the which tutorial package they use, but the variability will be possibility for the different for the particular package what the students used. There should be some variability also for every package they used it. So, the analysis of variance in short form it is ANOVA, ANOVA. Taken a few letters from the analysis of variance, in short form it is called ANOVA, is a technique that can be used to check such hypothesis. So, how we are going to do that is the equality of 2 or more proportions or treatments by means by analyzing the variance of the observed sample. We are going to test the equality of 2 or more proportions 2 or more populations means by analyzing the variance of observed samples. We are going to analyze the variance of observed sample, but the statement is about the null hypothesis statement is about the equality of 2 or more populations means. This is the difference between the testing of hypothesis regarding the population mean and analysis of variance or ANOVA. In both the places, whenever you have more populations, the null hypothesis look like same both in testing of hypothesis regarding the population mean as well as testing of hypothesis via analysis of variance or ANOVA. In both the cases the null hypothesis is look like same for more than 2 or more proportions 2 or more populations. the population means are same, that is the hypothesis. But in the analysis of variance, we are going to analyze the variance of observed sample to conclude whether the population means are same or not. But here the population should be minimum, it has to be 2 or more, whereas for 1 or 2 proportions and so on, you can do it with the testing of hypothesis regarding the means, whereas here you need minimum 2 proportions to analyze the variance of the observed samples. Yeah. You need a minimum 2 populations or more populations to analyze the or to make the null hypothesis of the population means are equal, and the alternate hypothesis is the population means are unequal. It allows to determine whether the difference between the samples are simply due to the random errors or due to the systematic treatment effects that cause the mean in one group to differ from the mean in other case. So, here the conclusion is different than the way you do the testing of hypothesis with the population mean in the first part what we have done, that is different from this. Here we are going to analyze via the variance of the observed samples, that is a very important concept. So, the theory and mathematical analysis behind the ANOVA, we have k distinct populations, and the null hypothesis is population means are going to be same for those k distinct populations, and alternate hypothesis is at least one pair of population means is significantly different. In the ANOVA test, we want to compare between group variance and within group variance, that is a very important concept. Therefore, we will compute these measures also. Let the group mean that denoted by x bar suffix I. So, we have k such groups, therefore, we have to find out the group means for each group divided by n, and the grand mean is going to be x bar suffix g, that is 1 divided by capital N double summation x I j, where I is running from 1 to n and j is running from 1 to k. That means we have taken sample of size n from each populations, we have k such populations. So, each population you have taken a sample of size n, therefore, your total sample size is going to be k times n, that you treat it as a capital N. You keep a capital N is a k times n, because we have taken sample of size small n in each populations, we have k such populations, fine, or k groups. As all the samples are of the same size n, therefore, you can get the grand total mean by using this formula also, correct. Since there are total of k times n independent observations. These are all the two quantities also you have to compute, because using these quantities only we are going to create the test statistics later. So, the one is called the sum of squares between with the suffix notation small b. Similarly, sum of squares within, that I am going to make it as a w in the suffix. The way I have written, you can be able to understand what is the sum of squares between and the sum of squares within. and the second is also called the error term, because you are subtracting x I j minus the x bar I the whole square. So, that is basically a error term. Similarly, you compute the third quantity, that is called the sum of squares of total, that is by subtracting x bar g then whole square with the double summation. You can easily able to conclude the sum of squares between plus sum of squares within, that is same of sum of squares in total. That means, if you compute any two quantity, you can get the third quantity. Now, we are going to introduce a test statistics, but before that you should know what is the distribution of each one, that you can able to identify. Based on our earlier discussion and so on, you can able to conclude that is SSB is going to be a chi-square distribution with the k minus 1 degrees of freedom, and similarly you can conclude SS within, that is also chi-square distribution with k times n minus 1 degrees of freedom, k times, because you have k groups or k populations, but multiplied by n minus 1 because you are using the sample mean. Therefore, the independent observations are reduced by 1, therefore, you will have a k minus 1 times n minus 1 times k, that is going to be the degrees of freedom for the sum of squares within. Now, you can create a test statistics by making mean square between, that is a ratio of SSB with the degrees of freedom, corresponding degrees of freedom. Similarly, mean square within, that is going to be SSW divided by degrees of freedom of W. So, now you can able to use the yes. So, now we have made the mean square between as well as mean square within. Using these two quantities, you can able to create a statistics, that is called F distribution. You can able to create the statistics, that is F distributed with the numerator degrees of freedom is k minus 1 and the denominator degrees of freedom is k times n minus 1. Therefore, the way you created the ratio of this mean square between and mean square within, you will get F statistics with the k minus 1 degrees of freedom and capital N minus k, or that is same as small k times n minus 1 degrees of freedom. Once you identify the test statistics, then the remaining procedure is same as what you have done it earlier. You can conclude the null hypothesis will be rejected if the value of the test statistics lies within the critical region, and this is a one sided test. This is a one sided test. Therefore, you will have a, if f naught value is greater than or equal to the point in which the right tail probability is going to be alpha, you can conclude the null hypothesis will be rejected. So, this is what we explained, that is a one factor experiment. This test will works quite well even if the underlying distributions are non-normal, unless they are highly skewed or the variance are quite different. In these cases, we need to transform the observation to make the distribution more symmetric about the variance. So, that is a one remark whenever you have such a situations. Here I have given a very simple example, and you want to verify whether the population means are same or different with the 5% level of significance. using the method of ANOVA. So, the data is given. So, you can proceed further. H naught is mu 1 is equal to mu 2 is equal to mu 3 and H 1 is at least one pair of means is significantly different. Then you compute sum of squares between and sum of squares within. Then follow other steps, that means create the F statistics, then find the value of F naught, then you conclude. So, in this problem this is null hypothesis will be rejected. With this we are completing So, all the calculation steps I have given one by one. So, you can verify whether you are getting the same results. So, using this F naught value, you can conclude the null hypothesis will be rejected. As a remark, whatever we have given, that is a one factor ANOVA, and extension of this is going to be two-way ANOVA. We are not going to explain two-way ANOVA technique in this course. So, we are stopping with the only one factor. Therefore, the testing of hypothesis with the one factor analysis, one factor technique, we have done it here. So, now we discuss the review problems on this topic. Question number 1, the chi-square test measures which one of the following? There are 4 options: mean deviation, goodness of fit, trend, variation. So, the correct answer is goodness of fit. Chi-square test measures which one of the following? The correct answer is goodness of fit. Now, we will move into second question. Probability of rejecting the null hypothesis when it is true is named as. The question is probability of rejecting the null hypothesis when it is true is named as. Type 1 error. We are finding the probability of type 1 error. Third question, the probability of type 1 error is referred as. There are 4 options: alpha, 1 minus alpha, alpha by 2, 1 minus alpha by 2. The correct answer is alpha. The fourth question, a failing student is passed by an examiner. It is an example of. There are 2 options. It is called a type 1 error or type 2 error. The correct answer is type 2 error. Move into the fifth question. A statement made about the population for a purpose of testing is referred as a hypothesis. A statement made about the population for the purpose of testing is referred as a hypothesis. Question number 6. Hypothesis testing of two population variances involve which distribution? Hypothesis testing of two population variances involves which distribution? There are 4 options: chi-square, f, t, normal. The correct answer is f distribution. Hypothesis testing of two population variances involve f distribution. Seventh question. Testing of hypothesis, that is null hypothesis, is population mean is equal to 30 against alternate hypothesis, the population mean is greater than 30, leads to whether it is called a left tailed test or right tailed test or two tailed test, or some books uses a two sided test also, left side or right side or two tailed two sided test. The correct answer is right tailed test or right side test. Testing of hypothesis, null hypothesis mu is equal to 30 and alternate hypothesis mu is greater than 30 leads to the right tailed test. With this we are completing the testing of hypothesis, starting from population means, then population variance, then population distribution, then further contingency table, and then proportions, finally the ANOVA method. Thank you.